Yeah, great. Thanks for having us. We are from DCSO. We are a company in Germany. We mainly look after big business, and we use SuriCata actually quite extensively to monitor our customer networks. And we are a managed security provider. So yeah, we put sensors in our customers' networks, and we analyze the data in our backend. We mainly focus on incident response and threat intelligence. That's our back office tasks. We have a SOC who analyzes the data for our customers. And and our sensors are a really important part in our customers' networks to get the right data to our analysts. So we mostly focus on advanced attack stuff, so the whole thing we call APT nowadays, or it's not a cool buzzword anymore, I don't know. We love SuriCata. We used SuriCata before DCSO was founded, so DCSO is only a 3-year-old company, so we've been in previous engagements where we also used SuriCata as a go-to tool to analyze network traffic to find attackers and attack paths in networks. And we don't sell sensors, so we are not a product company like some other companies. We only use them as an important tool to do our service. So, building a security service the last 3 years has been a huge challenge, especially because the companies we're dealing with are the biggest companies in Germany, actually. And so we had huge amount of traffic to go through and some various other challenges we would like to talk to you about today, because some of this stuff is actually applicable to probably most of your usages of SuriCata today. And we will have a little surprise in the end. So, let's get started. One of the biggest challenges we had with when we started, especially with growing bandwidth in our customer networks, has been traffic acquisition. It's also been a part of the training we had with Eric and Pevma this week. And so we started off with AF Packet. We used PF-ring after some time, and with all the cool stuff coming up in the Linux kernel with recent versions, we will be probably going back to AF Packet with AF-XTP, and we recently dropped PF-ring from all our sensors because the thing is, with having sensors all over the world and all over the globe, actually, we realized that playing with your kernel the way PF-ring does may lead to failures that give you a really expensive brick hanging in someone else's rack, and maybe you don't have a helicopter to fly there and fix it. So one of the things we learned the hard way was don't play with the kernel. Actually, and also the new features that are coming up with AF Packet, AF-XTP, will play very nicely with our X710 Intel cards we're using. So we use off-the-shelf hardware for all our sensors. We don't use any capture cards or something like that at the moment. And it works pretty well to a certain extent.
Okay, let me quickly continue with another challenge that we were facing, so getting the sensors actually to the place where they belong. So as you can imagine, most of our deployments are quite unique. So we've got lots of customers in different data centers, and they have different IP ranges and so on, different home networks, external networks, and so on. So that means we also have a lot of different SuriCata configurations, right? But in order to get all these sensors out there in time, we need some way to speed up the process, do some kind of automation here. And I think we've arrived at a very nice place now using Debian as the basis for the software stack. So we can use preceding, which is basically a way to do unattended installation on Debian in a very structured and time-tested way. And on top of that, do deployment of our own custom software stack with Ansible. And this really turned out to be the way to go for us, because it enabled us to put a lot of sensors out there very quickly. That means all we need to do when provisioning a sensor is just put in IP configuration for the management interface, because in companies like these are usually static and have to be agreed beforehand, and that's the only manual step that's required at the moment. When it comes to network interface types, so do we use copper, Ethernet, or fiber, and so on, we found out that the best way to do is just to have one model. Don't differentiate there at all, just have multiple interface cards on the hardware, so move the variation into the hardware, configure Suricata to listen on all of them, and do all the fine-grained configuration later when we know what's actually being used at the customer site. There's also a piece of software that helps us doing that. We will come back to this later. And all the baselining steps will then be done in an automated fashion later as well when we actually see traffic there. As I said, we'll come back to that. Another thing we had to care about at some point was what do we do with the data that actually gets generated by Suricata, right? Everyone starts out with ELK, Elasticsearch Log/Kibana. Their first idea was just to store everything on the sensor, and then if we need to know anything, just connect to the sensor, use Kibana to look at stuff. But that works if you've just got some low traffic sensors. As long as things move up a little bit, that won't really scale a lot. So we tried different other on-sensor persistent storage engines. We used MongoDB. We tried to use PostgreSQL with delayed indexing, bulk inserts, and so on. That seemed to work a little bit, but still that gave us problems when trying to query these things in an automatic fashion later. So at some point we just said, we can't going to abandon local storage at all. We just try to do what we need to do with the data on the sensor, move on from the sensor, what we need to have in the backend, and then that's it. And we found out that in order to arrive at maximum throughput, having the Redis output option in Suricata was very helpful, because that can act as a very nice buffer to feed things into our downstream pipeline. On the backend side, actually acting on the data that we get, we first started with NiFi to receive the data, do some processing on them, and move them on to where they need to be. But we weren't really happy with the performance there. So at some point, we decided to just use something simpler, try to lock with RabbitMQ, and that really stuck around until now. Both performance and functionality was really convincing for us, so we stayed for that. So since we have such a big variety in customers, some of them don't really have the bandwidth necessary to push everything towards our backend. So if you've got control over the sensor and placement and environment, that's fine. Just point everything at your RabbitMQ. Don't care how much it is, but that doesn't work for some of our customer sites, because some of them only have a couple of kilobytes of upstream traffic. So since we can't store everything on the sensor and we can't send everything home, there has to be some kind of compromise to be made. And we found out that what we need to do is have some way of quickly deriving a way to work with data on the sensor side. So do what we need to do at the source where the data is generated. So that's mostly alerts as well as metadata from Suricata protocol parsers. And we wrote a little software tool called Fever that allows to write small pieces of code in Go that can be executed on a stream of events that gets received from Redis or any other input. And that can be used to store things, to post-process things, to generate new data, and basically structure it in any way that we want, and then send it off to a separate channel. And also, using RabbitMQ in the backend allows us to have to scale up the number of consumers, so of components that work with the data. If we found out that something lags because it can't process things in time, we just put in more software components reading from the same exchange. And I mean, this is a very nice way to actually structure the way data is handled in the backend and to scale up if necessary. So this is an example for how we actually process data at the moment. We've got Suricata producing EVE-JSON, which goes into Redis on the sensor. And then using the Go library ReadyGo, we just pull out things into Fever, where there's a dispatcher loop that basically traverses over the data that's in there. And then each individual component can subscribe to a specific event type. So for example, if you have a something that does PDNS, that's only interested in the DNS events and so on. We have a Bloom filter matcher, for example, that allows us to match against huge sets of IOCs, which then, if there's a match, will forward an alert or generate a new alert that didn't originate in Suricata but originated somewhere else on the way. And so on. And it's very easy to plug in new code in there. So you could just write another piece of Go code, implement a couple of interface functions, and then compile the whole thing and point it at your own data sinks. And then on the back end, we have a couple of exchanges, and all our internal consumers can then subscribe to these exchanges. So you can have one exchange put things to multiple towards multiple consumers. So that means each of them will share the data, and you could also have one consumer pull in data from various exchanges. And we have buffering in between as well. So if one of the consumers goes away and there is a persistent queue, we won't lose anything. So what can we do with this? So sometimes we tend to know the networks of our customers better than the customers actually do themselves. It is very useful for analysts who look at alerts to find out what kinds of assets or hosts they're actually looking at. So first of all, we do some kind of passive network enumeration. So that means if we see an IP address, a host on the network, we annotate it with a tag. So is it an internal host? Is it an external host? Is it a proxy server? Does it serve any particular kind of protocol? And we found out that it's enough to actually look at flows. So pairs of source destination IPs, destination ports, and if it's an HTTP request, just look at the host header in there. And then once we've got annotations of individual hosts, we can broaden the whole thing into network ranges and try to replicate a higher level view of the customer's network. And if the customer knows something more about the network, for example, where each of these IP ranges is physically located, we could just add that data in there and present the whole thing as one unified view to our analysts. And on the other hand, we also do passive DNS. So we basically have tuples of DNS replies at some point, count them, aggregate them over a time period. This is a 1 minute typically for us. And then we've got a server on our own backend that we've written for that purpose that would answer questions given as a GraphQL query. And we're also releasing this piece of software later. There will be an additional announcement. And Paul Vixie and some people from the Circle, I think, came up with a common format to actually return this data from a server, and this is also something that we implement. So if your software or your observable integration framework can consume this common output format, it will be able to work with our backend as well.
Yeah. So for the data processing side, another thing that we realized when we looked at large networks was that we had to do sensor baselining for every single location. So we ship a common default setting that we think is a good tuning for Suricata, but we have to actually do remote tuning of every single sensor, especially when you're dealing with large bandwidth, let's say up to 20 gigabit or more. You have to do specific baselining per location. And we had a lot of like tuning advice, and we tried to put everything together. And also we try to fill the variables that are used by the ET Pro rule set or our own rules, be it HomeNet, proxy service, domain controllers, with the information that we gather from the passive network enumeration service that we build. So to put everything together, we try to automate the whole process of sensor baselining to a certain extent so that bringing out a sensor to a customer location with minimum packet drops and everything like that, we try to automate everything away and automatically generate the YAML files that are necessary to run Suricata. Yeah, and we actually do that. So we use all the information that we have about the customer network and the traffic shape and stuff like that, and just generate the YAML files and let the engine do the rest. Yeah. because baselining is also not automatable to a full extent because we don't control the network input. So our customers, most of them actually use SPAN ports to feed us the data. We know it's not perfect, but that's the way it is. And we have to deal with switches that are over-provisioned, so they drop packets before they get to our sensor and stuff like that, but we try to make the best out of it. And we also try to tune this so so that we are able to detect more. We have a tool called SlinkWatch that tries to automatically detect when our customers connect the capture cables to our appliance, and then look at look at the link and automatically generate the necessary YAML files and restart the Suricata service to only include the specific port at the specific card of our appliance. Because when you configure workers in Suricata, and we only have a limited amount of CPU cores in our appliance, you don't want to pre-provision a fixed set of worker per NIC if the customer only uses one NIC. So we try to generate that on the fly based on the cables that are connected.
Right, so we can see that lots of things go wrong, whether they be in our own responsibility or not. So it's, at some point we need to have a means of finding out when things go wrong and what goes wrong exactly. So we actually, in an ideal world, we find out about these things before the customer does and calls us if something goes away. So we needed some kind of monitoring infrastructure. So I'm not really sure how all of you monitor your sensor installations. This seems to be something I haven't really been able to find a lot of information about. So I'm just going to quickly walk you through how we're doing it. So let's say we have a couple of sensors, each of which is running Suricata. And what we want to know is Suricata actually running and how is it behaving? So we use Telegraph, which is part of Influx Data's TIC stack, to receive data from Suricata via a socket. So that's basically the whole stats set of counters. And also we get some additional statistics from Fever. So for example, how many events have been observed or have been dispatched, how many flows have been seen, how much of this has been aggregated, what's the state of a Redis queues, and so on. And all of this gets moved into a specific metrics exchange in the RabbitMQ, where from there it gets passed on into an InfluxDB instance, as well as into a piece of software called a capacitor. So InfluxDB is a time series database that's optimized for storing this kind of numeric performance data. And is really fast in both ingestion and also answering queries or aggregating queries on these data. And capacitor is some kind of online alerting engine that allows you to specify specific conditions on a time scale, and then just alerts you if one of them fires. So for having an historical view on how things were behaving at a specific point in time, InfluxDB is very nice, but capacitor is good to give you online or real-time alerts if specific conditions are met or not. And then to look at the whole thing, our engineers can use things like Chronograph, which is a visualization engine for the whole thing, or Grafana to build dashboards that they can use in their daily work to monitor the performance of the service. So this is basically what Telegraph gives us in Grafana. Not sure if you can actually see it. So this is just basic data like, memory usage, CPU load, network performance, so how much bandwidth do each individual interface use, and so on. I mean, this is basically something that's not specific to Suricata, right? This is just seeing how the sensor behaves. But then having a patched version of Telegraph at the moment that also includes support for storing and aggregating the data from Suricata and from Fever. We also get additional data about the number of events, for example, the distribution of different protocols in the traffic, so we can see what's the traffic mix at one particular location. Does the sensor only see DNS, or is there a healthy mix of different various things? Does it match what the customer expects us to see or not? And also for debugging, we've had multiple instances of needing some internal Suricata data, right? For example, what are the flow counters like at a point in time? What are memcaps like? And so on. So these are also internals that we can plot in the same dashboard as the rest of the data. And this makes it quite easy to correlate certain events that are outside of our control with what we see in Suricata performance. And then for debugging, it's also sometimes useful to see data that doesn't really originate in Suricata at all. So things like the drop rate of packets on the NIC level, right? So is it something that can be tuned within Suricata, or do we need to look at a lower level, at the operating system level? So we also have a piece of software called ETHflux, which will expose all of the ETH tool counters for a specific network card driver to Telegraph, which can then be also viewed and graphed in a unified dashboard here. And of course, we can't just do this for a single system. We can also do this for basically all of our sensors in one long list. So that allows engineers who look or who are tasked with responding to potential failures of the sensor stack to see the overall health of all the deployments at one point, for example, and then look for example, for memcaps. So in this example, these are just 5 sensors. It's usually more than 50 in our case, but you can see that one of them on the lower right side has a memcap, and it's light blue, so that should be HTTP for us. So this is very easy to spot and then to react. Oh, and one more thing. If you're interested in having all of these functionality in upstream Telegraph as well, so if you just do an apt install Telegraph or get the software from Influx Data themselves, please vote for this merge request, which has been open for more a year now, because they are going to process these merge requests in order of demand. So if the more demand we can get, the better. Yeah. Thank you.
So we need your community help. You have all the notebook in front of you, or most of you have. So just go to the GitHub page and click on the little thumbs up on the left, so it gets bumped up. Thank you. It's actually, you have to look at the date. So Sascha submitted it in August last year. So we would really love to get it included finally. Yeah, so this was a little overview about the challenges we're dealing with. I hope that some of them are familiar and maybe we will have some solutions. We've come for 3 years now to learn some stuff to build managed security services around Suricata. And so the lessons learned for us actually are, the first point for us was automation. Automate all the things possible and keep the tedious tasks of your good personnel that can do better stuff. So we automated all the things, and Ansible came in very handy for us. Also, be the master of your own house. So what we mean by that, all the communication with our backend from every sensor is tunneled through a VPN. And this allows our customers to only need one firewall rule to get our sensor connected. And this makes it easy for them to not go through a huge manual and have 50 firewall excludes to get our sensor running. So the VPN for us is really helped to do stuff. RabbitMQ and message queue as a concept, apart from the tool itself, has been very helpful for us to prototype new analysis tasks in the backend. Because if an analyst have an idea to work with a certain if JSON data type, they can just connect to the RabbitMQ, do a temporal consumer, work on the data, and if it works out, we make a productive service out of it. So message queuing is awesome. You should all do it. If you have lots of data. Also, monitoring. We started off with basic monitoring like Zynga, and now we're really far with the whole Telegraph and Influx backend, and it helped us to spot a lot of errors in our stack. So monitoring is helpful, and you should also do it. And I know it's sometimes the last thing you build, or the thing you build when you start seeing things to fail. Yeah, start earlier. build your own specialized stuff. So we are a huge fan of open source, and we endorse it as much as possible. But we had the problem that we needed to build our own tools for certain tasks because we had a special need for it. And we tried to circumvent it in the beginning, but yeah, if you're getting bigger, you have to write some own tooling. But the important part is what to do with it. Also, a hard-learned lesson for us was to trust in the Linux kernel development and to keep up to date with the kernels and use the network stack properly. And I especially mean AF-Packet with that, so for us it works really well if you know all the ups and downs, which training can help. So. Also, we eliminated all the local storage from our sensors, especially when you want to do 20 gigabit processing of or more on a single hardware unit. You have to keep other stuff off the sensor as much as possible. So this has been also a lesson. And I also told open source is your friend. We're coming close to the end of our presentation. What are the remaining challenges? Rule management is still a thing that's kind of hard, so we try to work on that at the moment, especially when it comes to custom rules per customer and stuff like that. Yeah, we don't have an easy solution for that yet. Also, our incident response team likes to see all the data, all the things, and not only the aggregated stuff we do for reporting. So we might need an incident response mode or something like that in the future. As being from Germany, a lot of our customers have huge production plans. So OT, IoT protocol support is a huge upcoming interest from our customers, and we have to deal with that in some way. Hopefully with new protocol parsers written in Rust. Also, we are working on an analysis chain for the new file store version 2, and we plan to do a whole analysis chain for the extracted files for that. So that's something we are currently doing. So, and now for the cool part last.
Yeah, so we've been explaining a lot of how we wrote our own stuff to help with the problems that we face, and I spent the last couple of weeks polishing off the stuff that we had for open source release. So on our GitHub organization, you will find repositories for the individual components that we were talking about. So that means our fast event processor, so basically the framework for all the on-sensor data wrangling, our passive DNS server, this linkwatch tool to automatically enable, disable, and assign threads to network interfaces as they come and go. Our InfluxDB data gathering tool for the ETH tool, statistics, and something we didn't talk too much about in detail. We also have some kind of Bloom filter matching engine that we also wrote as a pod component. So that's not just included in Fever, but there's also a toolkit to build and maintain these Bloom filters. So we're also releasing that. And also it's going to be in Debian in the next release. So we've just uploaded everything to the Debian archive. It's just in the new queue, so sitting in line for approval and should hit the archive soon. So if there are any questions about this, both the software and our approaches, come talk to us. We'll be here all the time. So yeah, we'd be happy to answer any questions you might have.